Whether you're a Tesla investor, a fan of their products, or just a sucker for cool technology, this episode is for you. First things first, I've never been more flattered in my life. It's super clear that Elon Musk modeled the Tesla bot directly after me. Not only does it dance like I do, but it's the same height as me, runs at my speed, and even has my haircut. It's easy to get hyped about the Tesla bot, especially when it's so good looking. But the things that actually hyped me up the most from Tesla's AI Day were the deep dives into the different computer vision challenges they've been tackling and their implications for autonomous robotaxis. So I'd like to show you why I think it's game over for other automakers who think that they can solve full self-driving before Tesla. We've known for a long time that Tesla has a massive lead in terms of collecting real-world data to solve this problem. But I think AI Day gave us some of the best insights into how they're using all that data. When Tesla thinks about full self-driving, they're thinking about three things: safety, comfort, and efficiency. My guess is that safety is actually the most important, then comfort, and then efficiency. Elon Musk has repeatedly stated that the prime directive of the car is to not crash. Safety is all about following the rules of the road and staying the right distance away from other vehicles, pedestrians, and obstacles. In my opinion, comfort is actually the second most important because if the ride isn't comfortable, people won't want to get back in the car. Comfort means planning smooth maneuvers with high confidence so that the Tesla doesn't end up doing things like starting a lane change it won't finish, braking more often than necessary, or driving too aggressively or defensively. That means efficiency is really the third priority, where the focus is on planning safe and comfortable routes that can be completed with as little wasted energy as possible. Let's check out an example. Here's a Tesla planning a route to change lanes and make a left-hand turn through traffic. One plan could be to change lanes immediately. That results in braking sharply and ends up being pretty uncomfortable for the passengers inside the car because of this sharp change in velocity. The next plan it considers is speeding up and making the lane change further down the road. But doing that means it risks missing the left-hand turn altogether, since that plan has the Tesla moving pretty fast when it gets to the position it needs to be to make the turn. These two plans are actually extremes of all the possible plans that the car could consider. What Tesla's path planning system actually does is consider all the possible plans between them and then chooses the most optimal path. That means maintaining fairly smooth speeds as the Tesla changes lanes to make the turn. The Tesla full self-driving software is constantly optimizing its plan based on things like how close the path would bring it to other vehicles, the total time it would take to execute the plan, how often it would have to accelerate and decelerate, and how quickly, and so on. The final result is a dynamic corridor that Tesla is always choosing to stay inside of, and the boundaries of that corridor shift based on what's going on around the car. It's one thing to solve this problem on the highway, where the road is mostly flat and straight, and the cars are generally moving with the flow of traffic. It's another thing to solve this problem for city driving, where there are way more intersections, parked cars, pedestrians, and things blocking the Tesla's view of its surroundings. And that brings me to the thing that really blew my mind. Teslas don't just plan their own paths, they predict the paths of everything they can see. Check out this use case they showed as to why they need to run the planner on everything in the scene. I think this was the most impressive part for me. The Tesla is on autopilot and traveling down a tight road crowded with cars parked along both sides, cones, dumpsters, trees, and a turn that prevents the cameras from seeing very far down the road. That means that autopilot can't plan very far into the future. Now, watch what happens next. This may not look super impressive on the surface, but here's what's actually going on under the hood.
That was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side, but the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, OK, I have space here. This person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car.
So using the predictive path planner on everything in the scene allows Tesla's autopilot to be aggressive enough to be a good driver. It's able to see the oncoming car change its yaw angle. That's the angle between its nose and the road. It understands that that means that it's pulling over and giving the right of way back to the Tesla. So the Tesla changes its own plan based on this new information in real time to make it through this tight corridor. One of my biggest concerns for full self-driving was moving to cameras only and away from radar, because radar typically gets better range information and works at night when cameras have a harder time seeing. During AI Day, Andrej Karpathy pointed out just how good their depth and velocity detection is without radar.
We also saw significant improvements in our ability to estimate depth and, of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green. And we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance. And in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network. So we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us.
This is a massive deal because if you want to track stuff in the present and predict its motion in the future, you need to have a very good estimate of its range. You need to know how far away something is to understand how fast it's actually moving, and if it's getting closer or further away from you. This is really hard to do from single images in real time, but Tesla is obviously great at pulling that information from video. In addition to showing us that they're able to get radar-like performance without using radar, they also showed us how they can detect and track things that they can't always see. Here's another quick clip comparing Tesla's image processing of single frames to their video processing when it comes to tracking cars that they can't always see.
The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent. And you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that this is not a very easily visible part right now and doesn't actually take that into account.
Okay, it's one thing to be able to do this when the Tesla is stopped on a flat road and when it's sunny out. But my other big argument against vision-only systems was bad conditions like snow, fog, and rain. The way Tesla solved this problem is actually the other reason I think it's game over for other automakers. Tesla asked their fleet for every clip where things are falling off a vehicle and disrupt the vision of the cameras, and in 1 week, the fleet returned 10,000 clips of that happening. Only Tesla has access to so much data of such a specific use case, because it's their cars and their cameras and their software returning that data for processing. This is something Tesla's artificial intelligence could only solve because they have such a massive data advantage. And oh boy, did they solve it.
So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this.
My background is in computer vision and radar signal processing, and I was a naysayer when it came to Tesla moving to vision only. This whole channel is about data-driven investing, and I think it's important to admit when I'm wrong. Tesla's data just showed me that I was wrong about needing to use radar. This data makes it clear to me that Tesla will be able to find a vision-only solution to any of these challenges. I want to point out one other reason that vision only makes a lot of sense that everyone, definitely including me, wasn't really considering. If Tesla drops radar from the story, they don't need to simulate radar data when they want more data than their fleet can provide. Since the whole system is now vision only, Tesla can run a visual simulation of road conditions using a photorealistic physics engine and not worry about what the radars would see in each case, and that's exactly what Tesla is doing. They can use video game engines to simulate traffic with a high degree of accuracy, not just in terms of what things look like at different angles and how the sun casts shadows at different times of day, but also how different cars drive and interact in every type of road condition and configuration. The advantage of simulated data is that it has perfect labels, perfect measurements, and ideal geometries and boundaries. But why simulate data in the first place? You may want to simulate lots of different variations of a rare case that could be difficult to source. For example, people and animals running in the middle of the highway during high-speed traffic. Is this use case a little silly? Yes, but it could happen, and an autonomous Tesla would need to handle it if and when it does. Simulation also helps when data is difficult to label, like when there are hundreds of moving objects in the scene that are blocking each other, crossing paths, changing angles, and so on. This is really hard because of the labeling steps specifically, but it's super easy to do with simulations because every asset comes with the correct labels and bounding boxes already. The third case is interesting as well. Closed loop cases are when Tesla wants to see what a car would do in a very specific situation after certain actions have already been taken. Instead of asking humans to do a specific set of actions to help with these use cases, they can just simulate it and see what the full self-driving software would do. This simulation engine is the second reason why it's game over for other automakers. Remember, Tesla's solution is now vision only, so other automakers would not only have to translate all of this to their own cameras and where those cameras are placed on their own vehicles, but if they use radar or LiDAR, they'd need to simulate what everything would look like to those sensors as well. The first thing Tesla does is simulate everything as the Tesla cameras would see them. That means the noise profile, exposure settings, distortions, and motion blur effects are all based on Tesla's cameras and calibrations specifically. After simulating what their cameras would return, the data goes through a photorealistic rendering step with the goal of being visually indistinguishable from reality. This includes reflections from surfaces, halo effects from lights, and anything else that could trip up a camera. They have a huge library of assets including thousands of unique vehicles, pedestrians, props like trees, buildings, benches, fences, trash cans, and all the other items that you would reasonably expect to be on or near the road. Again, the goal here is to quickly be able to build thousands of usable datasets to help train Tesla's vision-only full self-driving algorithms for cases where there isn't enough real camera data. They can make as many of these variations for a given scenario as they need, with high confidence that what they're simulating is very close to what the real cameras would actually see in real life. Here's a direct comparison between an original clip and one that was rendered from the simulator. Imagine how cool it would be to play the next Grand Theft Auto game if it looked as real as this. So, there are two things that would spell game over for other automakers solving full self-driving before Tesla: the staggering amount of real-world camera-only data that Tesla can draw from their fleet, and the infinite amount of Tesla-specific simulated data that they can create whenever the fleet is somehow not enough. They use all that data to train the full self-driving software to plan optimized routes, not only for the Tesla cars themselves, but for everything the Tesla cars can see. They do that so they can make moment-by-moment decisions on how aggressive or defensive they should be in any given situation under any road condition. And of course, if all else fails, they can just throw a sweet-looking clone of me in the car and have it do all the driving instead. Comment below or tweet me your thoughts on Tesla's AI Day and any of the details they shared. I barely scratched the surface with this episode, so let me know if there's something else that you want me to cover. Either way, I hope this episode helped you understand how Tesla's massive real-world data advantage and their full self-driving data simulator combine to spell game over for other automakers that are relying on less scalable and more expensive sensors like radar and LiDAR to solve this problem. If it did, consider investing in the like button and subscribing to the channel with all notifications turned on. That's a great way to invest in the channel that invests in you, and get me into a sweet Tesla robot suit. Seriously, how do I get one of these bad boys? Until next time, this is ticker symbol U. My name is Alex, reminding you that the best investment you can make is in you.